So here's a little review on polar graphing that if you were in advanced pre-calc last year, you've all seen. Not that I expect you to remember every bit of it, hence the video. If you have notes from last year, if you can find somebody who does have notes from last year and copy them, there's a lot of shortcuts to this, but bottom line, I don't need you to be that proficient in graphing quickly, but just being thorough. So here we go. I've got the equation r equals 1 plus 2 cosine theta, and I'm putting in values for theta: 0, pi halves, pi, 3 pi halves, and 2 pi. And as long as your coefficient in front of theta is 1, like it is in this problem, those values of theta should be sufficient to graph the entire curve. So here's going to rely heavily on your unit circle knowledge, so I've gone ahead and filled out the chart. You should be able to follow that. So here's how to graph in polar. We're pointed toward 0. 0 radians, 0 degrees, it's all the same. And our radius is a positive 3. So I'm going to go out 1, 2, 3, and there's my first point. My second point is pointed toward pi over 2. And that has a radius of 1, so there's my second point. My third point is pointed toward pi, so I'm at 180 degrees looking to the left. But my radius is negative, and that really doesn't mean a negative length. It means a length of 1 and a direction that's negative. So I always explain this in years past of walking backwards. So you're pointed toward pi, but instead of going toward pi 1, you're going away from pi. So there's my third point. 3 pi over 2 is going to put me at 1, and then 2 pi puts me back to 3. This is the polar graph that creates a loop. So you're going to see me go like this, through the origin, loop, back to the origin, and there's the graph of my polar curve. Last year that was good enough. You were good to go. Some things that we're going to look at specifically. It took all the way from 0 to 2 pi to create the full curve. We're going to be able to use that to be able to find area, because you're going to need to know the alpha and the beta that creates the region that you're being asked to find the area of. A tricky problem would be, what if they just wanted you to find the area inside the loop? We're going to get to that next week, but for right now, you need to be able to tell me the angles that actually form the loop. When does it go through 0? When does it come to -1? When does it come back to 0? And this is like a trig equation. You want a radius of 1, so 1 plus 2 cosine theta equals 0. Cosine of theta equals -1/2. So what values of cosine are negative? That would be hopefully you remember, all students take calculus, second and third quadrants. So theta would be 2 pi thirds and 4 pi thirds. So if we had actually included these in the appropriate spot in our T-chart, you would have gotten 0 and 0. So from 2 pi thirds to 4 pi thirds, you get this lovely little loop. And from that, later on, I'll teach you how to find the area just inside the loop. We may come back to this very example. Another real popular type of polar is the one that creates petals. And here we see that the petals are always going to be the ones that have a coefficient in front of theta other than 1. So how I adapted my T-chart is, instead of just going from 0 to pi halves to pi to 3 pi over 2 to 2 pi, I included the pi fourths in between, which would give me then times 2 those specific angles that we got back before. So again, I filled out the chart for you. This is again just using unit circle values, and so let's graph it together. We start off at 0, 0. When we're pointed towards 0 degrees, we don't go anywhere. Our radius is 0. But we get up here to pi fourths, and we have a radius of 3. and then we come back to 0. That is a petal. There it is. If we had put in lots of other values like pi-8ths and pi-thirds and pi-6, we would have gotten really nasty values of r, but I promise you our petal would look something similar to that. Now when we're over here at 3 pi-fourths, so I'm in the second quadrant, notice that here my radius is negative again. So I'm down here. Opposite 3 pi-fourths is 7 pi-fourths, so that's 1, 2, 3. So where we just went from here to here, now we're going to come down here and then back to 0 at, where are we back to 0? Back to 0 at pi. For 5 pi-fourths, down here in the third quadrant, we get another positive r at 3, so 1, 2, 3. We just finished up that second petal in the fourth quadrant, and we're making a third petal in the third quadrant, and then finishing up at 7 pi-fourths, we get the last negative, which is going to give you the fourth petal, up here at 3 pi-fourths. So the interesting thing about this that you need to just remember that when your coefficient in front of theta is even, it doubles the number of petals. That's one thing to remember. The petal length is always the coefficient in front of sine or cosine. What's going to happen here, again, when we're talking about petal length or area under the petal, which is what we're going to deal with next week, you really only need one petal. If we wanted the whole thing, they're all the same length, you can multiply it by 4. So that's really the important thing, that it takes from 0 to pi halves to create one petal, and all the rest of them are of the same length and of the same area, and they split evenly into the 4 quadrants. I can imagine when you graphed it last year in advanced pre-calc, we didn't really care the order in which it traveled. We just went boom, 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 boom. But as you can see from our chart, it starts in the first, goes into the fourth, goes into the third, and then finishes up in the second quadrant. So that's kind of cool. Hopefully this will help you. Again, a T-chart is great. I would get out your calculator and make sure you can put your graph in polar mode and be able to graph one of these yourself. But as you're doing it, pay attention to the values of theta that will either create the whole graph, or in the case of petals, what would create one petal. See you all either Friday or on Monday.